All right, good morning and welcome to this short demo video about Optix. This is an optimization tool that's put out by our lab, and we hope you find it useful. To get to Optix, you're going to go to the USU AeroLab website and click on Tools and go to Optimization. And this is the main page for Optix. In order to get the source code, you're going to click on this link that'll take you to GitHub. And once we get there, you have two options for downloading Optix. You can either clone the repository, which is my preferred way of doing it. You do that using this URL here, or you can download a zip file of the code and just extract that onto your local machine. Either way works just fine. Once you get it onto your machine, and I'll show you the GitHub way to do it real quick, you're going to go and you type git clone and then that URL you just barely saw, so www.github.com/usu/aero/optix. And mine already exists, so it's not going to re-download it, but that's what you do. You'll go then into the Optix directory, and once you're there, you're going to run the command pip install dot. For some of you, the command will be pip or python-m pip install dot. Just kind of depends on your machine. You can and on I guess your Python installation, but you can find that. Anyway, now it's installed. You really don't want to skip this installation step, because what this does is it means that from anywhere on your machine, you can go into Python and you can import Optix as a package, or I guess as a Python module. So that makes it so you don't have to be copying your source code around. It's just a lot easier for you. I'll show you now how you can get to the documentation for Optix. If you're in a Python interpreter, then you can do import Optix and then type help optix.minimize. All of the functionality for Optix is wrapped up in this single function minimize here. So if you click enter on that, then this shows you the doc strings for this minimize function, and it gives you a basic idea of how this works. Now, Optix is a library for function minimization. One of the big advantages of it is that it uses native multiprocessing. So if you've got if you're running some kind of model, your objective function, takes a little while to run, then in any instance where Optix can run multiple objective functions at once, it will. And so it takes advantage of multiprocessing in that way. So this is what the documentation for Optix looks like, and basically all you need at the most basic level is you need a function, which is a Python callable, that is your objective function, the one you want to minimize, and then x naught. This is a starting guess for your independent or your design variables. And then everything else is really optional, but you have a lot of power that you can, you have a lot of power in what you can specify with these optional arguments. Args you can use to pass additional arguments to your objective function. So say we've got an objective function here, and imagine this is some kind of like some compressible fluid flow code, where maybe your design variables are Mach number and wedge angle. But all of those properties are all of your flow properties are going to be a calculation of, or a function of gamma. But gamma you don't want to be a design variable, because you're probably just going to be flying in the atmosphere, so it's 1.4. But if you want to be able to change that, then you can include gamma as an argument here, and in your function definition, and then here you can pass it in as part of this args, and Optix will keep track of that for you and supply it to your objective time each time it's called, or your objective function each time it's called. And then you have a few different methods available to you. There's one that's not listed here, which is null or meet, and we'll talk about that in a sec. But you have unconstrained problems, you have constrained problems. If you don't have constraints, you can use what's called BFGS, which is a quasi-Newton's method. It's very popular. Or you can use the Nelder-Mead algorithm, which I'll talk about in a little bit. For constrained problems, you can use either SQP or GRG. Also very popular algorithms. GRG is the one that's implemented within Excel, and SQP is probably one of the most popular, most effective methods that's built into the SciPy minimize library. Anyway, you can also pass it a function called grad that will give it the gradient of your objective function. So if you can analytically calculate gradients, or if you've got a better way to do that than finite differencing, then you can pass it in. Otherwise, Optix will just handle the gradient calculations using finite differencing for you. You don't have to specify that. You can also give it constraints, and I'll talk when we go into the demo, I'll talk more about what those constraints exactly are. You can control the termination tolerance, so how small does the step side needs to be in order for it to quit, how small does the gradient need to be for it to quit. There's a whole bunch of just different ways you can tweak with the optimization, and I won't get into into all of these, but I just wanted to give you a basic overview, and that these are here, and this is how you find out what they are. For each one of these different methods, there are a few specific arguments, just because each one is doing different things under the hood, and there are different knobs that you can turn depending on which method you use. So that's it for the documentation. Let's go and look at how do we actually use these. I'm going to go into my documents folder, and I've created a couple demo Python scripts here. So again, because we've installed it, doesn't matter where we are, we can just do this import command. So import Optix as opt. And then here in my main section, I've defined a function that I want to minimize. This is a really just simple two-dimensional quadratic. Going to make our life really easy and make the life easy for the optimization algorithm. You'll find that depending upon the behavior of your objective function, some algorithms work better than others. You'll have problems for which SQP converges really, really well, but GRG doesn't. And you may have problems for which, Nelder-Mead does a great job, but BFGS doesn't, and even the other way around, it just depends. But your call to Optix is going to look like this. You're going to say the return from this function is a class. It's kind of just a data container. It'll contain like your objective function at the final iteration, what the location of the optimum point is, and a couple of other things, and that's all again explained in that doc string. You call opt.minimize, you give it your function that you want to minimize, you give it your initial guess, which I've specified here. Your initial guess can be either a list or a NumPy array, it doesn't matter. And then for this one, I've told it I want to use the BFGS algorithm. I don't have any constraints specified right now, and then I'm going to give it a termination tolerance of 1 times 10 to the negative 12th. Now you don't have to specify the method. If you've not given Optix constraints, or if you've not given minimize constraints, then it will automatically pick BFGS. If you have given it constraints, it'll automatically pick SQP. So you don't have to specify the method, but here I've just done it to be painfully explicit. Anyway, so that will run the BFGS algorithm. It's all wrapped up in that single line, really straightforward. And you can see, and this has been intentional, we've tried to imitate the structure and the syntax of SciPy Optimize because they've done a good job with it. And then we'll just plot out the result. I'm going to plot the optimum point against some contours here. So we'll just run Python optixdemo.py. And so this is the output from Optix. It'll give you quite a bit of information here. If you tell it to be verbose, it'll give you even more information. But it'll make, so this is so you can make sure you're doing everything right. It'll tell you your initial guess, your initial step size, the stopping, the step tolerance for quitting, whether or not you want it verbose, just a whole bunch of different parameters it displays here. And then it'll give you information regarding these iterations that it's going through. And at each iteration it'll tell you the fitness, so that's your objective function, your fitness function. MagDX that's the magnitude of the step that it's taken from the previous iteration. And then these are the design variables at each step. So we can watch it's walking along, and it's decreasing in the objective function every time. And once we've gotten to the point where our step size is really, really small, it's decided, okay, I'm done. And it says, okay, this is your objective function, or this is your minimum point, or minimum objective function, and this is the design variables at that, or that will give you that minimum objective function. We've plotted it here, and you can see it's done a great job. Obviously, you could just look at this and say, oh, well, yeah, the bottom of this function is 0, 0, and the result is going to be 0, so why did I need a minimizer for that? And again, I've chosen this kind of pedantic example just so that we can see clearly the optimizer is doing what we would expect. You can obviously give it much more complicated objective functions. It probably won't converge as quickly as it did for this one, but it should still converge. So that's what the output from a typical run of Optix looks like. Before we move on to specifying constraints, I'll show you how to use the Nelder-Mead algorithm real quick. So we can switch over to Nelder-Mead. The interesting thing about Nelder-Mead is that it is a gradient-free method. So at no point does it actually calculate any gradients. So you can run it on data that is discontinuous, not necessarily discontinuous in domain, but discontinuous in range. If you've got step functions, if you've got cliffs and valleys in your data, then you can use, or in your objective function, you can use the Nelder-Mead algorithm on that. But if we just run it on the same one as we ran before, it's really fast. You can see it's taken a lot more iterations to do what it needed to do. But again, it's not computing a gradient at each step, and it's not computing a line search at each step. And so it goes a lot faster. You can see we've not converged quite as close to the minimum point as with the BFGS algorithm, but we're practically there. You're below single precision here. So like I said, you can use Nelder-Mead in situations where BFGS isn't going to do as well. So if I were to come and make my data a little discontinuous here, instead of doing these variables squared, what if I called the absolute value of these, which if you remember, absolute value gives you a very sharp valley at the minimum point. And then here I'm just going to throw even more at it. I'm going to say this term I want rounded to the first decimal place. So let's run that with Nelder-Mead, and we're just going to see how it does. So again, if you notice, our objective function looks a little weird here, but Nelder-Mead has done just fine. It's gone, practically to 0 in both the objective function and in the design variables. If we were to run BFGS on this, clear that. It's struggling. You see it stepped really close to the optimum really quickly, but when you look at where it's gotten, it's not nearly converged to 0 in terms of the objective function, and then it's still quite a ways off from the origin. So that's again one of the advantages of the Nelder-Mead algorithm as opposed to one of these gradient-based methods. Anyway, let's move on to specifying constraints. I've just defined another script here, and again I'm just doing the same function that I want to minimize, but now I'm going to specify a constraint, and you do that using this right here. For a constraint, you need to tell it whether it's an equality or an inequality constraint, and then you also need to give it a function. So if you give it an equality constraint, then you're telling it whenever you call this function on x are the design variables, I want this function to equal 0. And so as it's running through, it will alter your design variables and minimize for things such that this function always evaluates to 0. So that's useful if you've got some type of constraint where you say, okay, I need I need the equivalent area distribution of some given airframe to be equal to this number, something like that. You can use equality constraints. You can also specify an inequality constraint. Here for type you just say ineq, and that means that anytime you call g, I want g to be positive, so 0 or above. And this allows you to bound in your design space and keep you out of regions that you know are infeasible. So you can define as many of these as you want. Now, I guess not as many of these as you want. You can only have as many equality constraints as you have design variables, which, if you recognize, if you've got as many equality constraints as you have design variables, it's no longer an optimization problem, it's a nonlinear system of equations. So that's you know, maybe you shouldn't be using an optimizer for a problem like that, but you can put in as many inequality constraints as you like. What Optix wants to see is simply a list of dictionaries where each dictionary contains one constraint and tells you the type and the function, and like with the objective function, you can also give it the gradient of your constraints if you know that analytically. If you don't, again, it'll just take care of it using finite differencing, and you don't have to worry about it at all. And then you pass it in here to the minimize function, just saying constraints is equal to constraints, and that's this list of dictionaries here. To start out, I'll use the GRG algorithm. Again, I've given a termination tolerance of 1 times 10 to the negative 12th, and then we're just going to plot the result against some contours. So let's look at this. We've got the same objective function as before, but we've specified an inequality constraint that we want x0 minus 1 to be equal to 0, which means that our minimum value for x0 is going to be 1. So we're going to be constrained to kind of the right half of our design space here. And let's run this and make sure that that's what's happening. Again, this runs quite a bit like BFGS. It gives you information about all the iterations, the step size, the design variables, but it's also going to tell you as it goes along what the constraint is. So you can watch as it goes along how it's satisfying these constraints. Now, it's really important to keep in mind the big difference between the GRG and the SQP algorithms is that the GRG algorithm will always stay inside feasible space. It will never violate your constraints. SQP will violate your constraints throughout the iterations. So if you're running an instance where, for example, your model is going to throw an error if you go outside of constrained space, or if your model might just quit at some point, you might want to use the GRG algorithm, because that ensures that you're never going to query a point out of constrained space, out of sight of feasible space. And even if you do, like if your machine crashes early or something like that, then the point that it's gotten to in the optimization is guaranteed to be feasible. Now, if you're running SQP, it could query points way outside of feasible space and it could break your model. Or if your machine is crashed partway through, you could end up with a solution that isn't at all feasible, and you've lost all that computing time that you've devoted. So this is the result that we've gotten, and you can see we've been constrained nicely to this line of x0 is equal to 1, and we found the minimum on that line. Again, this is an inequality constraint, so everything over here is in feasible space, but it's found the minimum right there within feasible space. We can do the same thing using the SQP algorithm. And we get the same result. Now you'll notice here, again, for these inequality constraints, it's specifying that this constraint either evaluate to a positive number or very, very close to 0. You can see that GRG ends up very, very close to 0. And SQP does the same thing. Depending on how our objective function is defined, how our constraints are defined, like I said, throughout for SQP, these values here could end up negative, and could stay negative for a little while. So you want to be aware of that. We can also specify equality constraints, like I said. If we turn that one to be an equality constraint, we'll probably get the same answer here, but we'll run it and we'll see. So again, we've driven to the constraint, we've driven to the same point, and GRG will do the same thing for you. So that's a basic overview of Optix. There's a lot more features that you can fiddle with, and those are explained in the doc strings. Please, if you have any issues with Optix, open up a new issue on the GitHub repository. That's the best way for tracking bugs, feature requests, anything like that. And we'd like to improve this. We'd like to make it a usable tool. Anyway, thanks for your time, and good luck with your optimization.